All right, okay. Thanks everyone for joining the session. If for any reason you cannot hear me, please let me know in the chat. All right, so today I'll be talking about the Applications Messaging Manager, which is a library or framework that allows intuitive and simple design of modular and scalable software. We'll first look briefly at what the solutions that come with LabVIEW out of the box are, such as queues, notifiers, user events, and the actor framework. Then I will present an example built with user events and then using the AMM for comparison. And we'll finish with some data on how the performance of the AMM changes with scale and the summary of its advantages. Before I begin, a short intro about my relevant experience. In my previous role, I managed a precision metrology lab at a scientific facility near Oxford, UK. There, among other activities, I developed a software to automate high-precision measurements of scientific motion devices using high-end metrology instruments. And currently, I'm working for Marelli, which is a leading automotive supplier, and where I lead the development of PC software used internally during the R&D process and the mass production and on the mass production lines of electronic control units. Just a note on nomenclature here. Please note that in this talk, I will be referring to software as meaning a collection of continuously running VIs with or without a front panel, where each VI performs a distinct operation or a set of operations. And although technically not correct, when using the words process, module, component, or application, I'm going to mean the same thing, namely just a continuously running VI. So when it comes to software, with the exception of just simple software, a key trait is that it requires multiple VIs to run in parallel. Now, these VIs require information from one another, so you must develop a way of effectively exchanging that information between them. The out-of-the-box tools that we have in LabVIEW are notifiers and queues, user events, and the actor framework for this purpose. Notifiers, queues, and user events are the basic building blocks for such functionality, but you must implement the communication mechanism yourself, and you have to do it every time for each new software. The actor framework is a solution built on top of such basic tools. Now, I'm not an expert with actor framework, but at a high level, it is heavily based on object-oriented programming in queues, and it uses a few user events for debugging purposes from what I've seen. And this is a great tool for building modular and scalable software, but its disadvantage is that it's difficult to master, so it's not something that you can pick up in an afternoon. Now, I'd like to walk you through an example of how you might implement information exchange between parallel VIs with user events. The code that I'll be presenting is simplified without much error handling to illustrate the point more easily. Let's assume that you have some external hardware and a PC connected together with a cable interface on USB. And you have a software with a user interface which can send commands to the hardware when a button is pressed and display the responses. You could structure your software something like this. You could have the command UI and the hardware. The command UI sends a command to the hardware and receives the response. But this architecture is not modular, nor is it scalable. So let's make it better. Let's put the entire hardware communication code into a separate module or application called communication module in this case, and have the command UI forward all commands to it and receive the hardware responses from it. You could structure the software something like this, using a producer-consumer design pattern with events. The event structure in the top loop of the command UI picks up the button press and enqueues a command for the bottom loop. The bottom loop triggers the comms user event to pass the command to the communication module. The communication module is subscribed to the comms user event. The event structure in the top loop of the communication module picks up the event from the command UI and enqueues the command for the bottom loop. The bottom loop then communicates with the hardware and triggers the response event in order to publish the response received from the hardware. The command UI is subscribed to this response event. It picks up the event from the communication module and enqueues a command for the bottom loop, and the bottom loop displays the result. And this sort of structure would work just fine. So your architecture would actually look something like this if you look at the block diagram. The communication module is subscribed to the comms user event, and the command UI sends the commands through this event, and the communication module publishes all hardware responses through the response event, which the command UI is subscribed to. But what if you want to add two more user interfaces to your software accessible through the window menu, for instance? One which displays a log of all the responses received from the hardware, and one which monitors a parameter of the hardware by periodically requesting its value independent of what the command UI is doing. Well, you could integrate them like this. Monitor UI sends its commands using the comms user event and receives the responses by also subscribing to the response event. And the log UI simply subscribes to the response event as well. I'm not going to show here the block diagrams of these two applications or modules, but the monitor UI would be implemented just like the command UI, and the log UI would just contain a while loop with an event structure. Now, the biggest problem with this implementation is that the command UI, the monitor UI, and the log UI still cannot exchange information between them. One possible solution would be for each app to have its dedicated user event reference through which it can receive messages. But this means you have to deal with a few things. You have to manage all those references and make all the references available for each app. You have to think about what happens when an app closes and then reopens. In this case, the initial user event reference becomes invalid. You would have many references in each app as the software scales. And for each new app, you would need a new dedicated reference, and you would have to add that reference in all the other apps. So it's doable, but it's a messy solution. Another possible solution would be to have each app use the existing comms reference in order to send and receive messages. Of course, for this, you would need to modify the data field of the event to include, for instance, the name of the sending application and the receiving application. And this solves the issue of dealing with multiple references, but it's not elegant because all apps will receive all messages, and each app receives its own messages. So it would be wasteful from the point of view of computational resources, potentially. And depending on what the apps do and how many messages are sent in this network, some apps might become glitchy due to handling all the messages that are not meant for them. So how about if you have a dedicated component which acts as a middleman, automatically managing all the necessary references in order to effectively forward messages between all the applications in the network? And this is exactly what the application messaging manager is. So let's see how this would work. The command UI passes a command to the AMM to be forwarded to the communication module. The AMM forwards the command to the communication module. The communication module sends the command to the hardware and retrieves the response. Then the communication module passes the response back to the AMM to be forwarded to the sender of the original command. and the AMM forwards the response to the command UI. And the monitor UI would send commands and receive responses exactly the same way. Yeah, Eric, you're exactly right. It's just a communication hub, essentially. How about if you wanted the command UI, for instance, to tell the monitor UI to start monitoring another parameter? Well, the command UI would just pass a command to the AMM to be forwarded to the monitor UI, and the AMM would forward that command to the monitor UI. In this case, you wouldn't need a response, but you could definitely implement one if you wanted to. The log UI could send commands and receive responses exactly the same way. And this mechanism would work between any two applications which are part of the network. Now, let's see how the log UI would work. Well, in the beginning, it says to the AMM, let me know when you have any notifications called data from hardware. And the AMM makes a note of this internally. Then let's assume the command UI performs its usual communication with the hardware as described previously. And now we have also programmed the communication module such that on top of sending the response to the command UI, it also packs the hardware response into a notification and passes it to the AMM for distribution to whoever is interested. The AMM looks internally for all of the apps which said they were interested and finds the log UI, so it forwards the notification to it. Again, this notification mechanism would work between any of the applications which are part of the network. Now let's see what happens when an error occurs in one of the apps. Let's assume that there was a communication error with the hardware. The communication module packs the error cluster into a broadcast message and passes it to the AMM. The AMM forwards the message to all the other applications in the network. And let's say we decided that monitor UI does not deal with displaying errors, so it ignores the broadcast message. We also decided the same for the log UI, so it too ignores the broadcast message. But we decided that the command UI is the application that deals with displaying errors to the user, so it will display the error in a pop-up dialog window. And again, this mechanism works for any application which produces an error. Now, let's see how the AMM is used in the code. We're only going to look at the communication module as an example, but all the other applications will use the AMM in exactly the same way. As you can see, it still uses the same design pattern, produce a consumer with events. And we're going to look at these three areas in more detail. In the initial stage of the communication module, we first initialize the AMM object. Or in other words, we obtain a reference to a network of applications with a certain name. In this case, the name is GLA. If the network doesn't already exist, it will be created and the communication module will be the first application which is part of it. If the network already exists, we will get a reference to it. Next, we register with the AMM to tell it that we want to be part of the network. We must specify the name of the application, which must be unique in the network. The function returns a handle and a set of user events, both of which are dedicated for the application that was just registered. Then we subscribe to the user events from the AMM. The message available event is triggered by the AMM when there is an incoming message. The message post error is triggered by the AMM if an error occurred while sending a message. This is used because messages are sent asynchronously by the AMM. And the stop event is triggered when the AMM object is closed, and all applications must stop in this case. And lastly, we go online. With this function call, we tell the AMM that the app is ready to receive messages. This must be called after registering for events, otherwise notifications about incoming messages might be lost. In the producer loop, of the communication module, this event case picks up the message available event from the AMM. We read the incoming message and send it for processing to the consumer loop. In the consumer loop, we have the process message case, where we look at the message name, and if it's send command, we communicate with the hardware. Then we pack the original message together with the hardware response and send the execution to the response and notification cases within the same loop. In the response case, we take the original message, change its type to response, set the sender of the original message as the receiver of this response, add the data, and pass the message to the AMM to be forwarded. In the notification case, we create a new message with type notification, set the name as data from hardware, add the data, and pass it to the AMM to be distributed. And this is the standard message structure. We have the name of the sending application, the type of the message. Here, command, acknowledge, and response messages are simply forwarded by the AMM to the destination application. Broadcast is forwarded to all applications in the network except the sender. Subscribe is meant to be consumed by the AMM and is used to change the notifications that an application is subscribed to. And notification is forwarded only to the applications that have subscribed to that notification. We have the name of the receiving application, the name of the message, which is user-defined, message options, which helps with further classifying messages that have the same name, the data contained in the message as a variant, so it can contain any data, the message priority. High priority messages are in queued for the receiver in front of normal priority ones, and the message identifier, which is just an integer that is used in pairing responses to commands. Now, I'd like to share some results on the average transmission time of a message through the AMM under 3 different scenarios. The first scenario was designed to mimic the maximum amount of strain that I would realistically expect the AMM to be subjected to in normal usage. So here I had a network in which each application continuously sends messages to other randomly selected applications at random intervals between 0 and 100 milliseconds. The message transmission time was measured each way, and all measurements were averaged together. This is how it works for one application. The application takes a current timestamp, wraps it in a command message, and passes it to the AMM. The AMM forwards the message to the receiver. The receiver takes the current timestamp, calculates the message transmission time, and stores it. Then takes another current timestamp, wraps it in a response message, and passes it back to the AMM. The AMM forwards the message to the original sender, which takes the current timestamp, calculates the message transmission time, and stores it as well. And the number of applications was varied in this network to see how the average transmission time changes. And this is the result. On the horizontal scale, we have the number of applications in the network going from 2 to 25. On the vertical scale, we have the average message transmission time in milliseconds. Now, given that the result varies here between 68 and 140 microseconds, which are quite small numbers, I wouldn't expect these measurements to be exact. And this is due to the normal jitter that you have in a PC, which is performing other tasks as well, which are scheduled by the operating system. The reason why I've gone only up to 25 applications is due to difficulty measuring the true transmission time without capturing any of the execution delays coming from the applications themselves. But the bottom line message of this graph is that the transmission time is negligible and scales well with network size. To put it into perspective, the transmission time of an event from generation to execution of the associated event case is somewhere between 10 and 20 microseconds. And the transmission time of a message through a queue from enqueuing to dequeuing is somewhere between 10 and 15 microseconds. The other two scenarios which I tested are a bit unrealistic for normal usage, but either way, I was curious to see what the limits of the AMM are. In the second scenario, all applications send a broadcast message into the network at the same time, and the number of applications is varied. In the third scenario, there is a fixed number of 10 applications which send multiple broadcast messages into the network at the same time, and the number of messages is varied. And again, the message transmission time was measured each way, and all measurements were averaged together. And this is how it works for one application. The application takes the current timestamp, wraps it in a broadcast message, and passes it to the AMM. The AMM forwards the message to all other applications. Each receiver takes the current timestamp, calculates the message transmission time and stores it, then takes another current timestamp, wraps it in a response message, and passes it back to the AMM. The AMM forwards all responses back to the original sender, which, for each response, takes the current timestamp, calculates the message transmission time, and stores it as well. And here are the results for the second scenario, with one broadcast message and a varying number of applications in the network. Again, on the horizontal scale, we have the number of apps going from 2 to 25. On the vertical scale, we have the average transmission time in milliseconds. And it doesn't look that bad. Below 7 applications, we are still in the microseconds range, and then we go into the milliseconds range. But at least the number doesn't skyrocket as the number of applications grows. As for the third scenario, with a fixed number of 10 applications in the network, the horizontal scale is logarithmic and represents the number of broadcast messages sent by each application, going from 1 to 500. The vertical scale is again the average transmission time in milliseconds. In this case, the performance degrades even more, going up to 875 milliseconds per message when you have 500 broadcast messages sent by each app at the same time. So, what are the advantages of the AMM over the alternatives? Remember that for notifiers, queues, and events, I said that you have to implement the communication mechanism yourself every time and manage all the references. Well, the AMM manages all of that for you, so you have to worry only about registering your application and sending messages. And the actor framework is difficult to master and takes time to learn. Well, the AMM is simple and intuitive, and you can get started in a matter of hours. So this brings me to the end of my talk, in which we briefly looked at the out-of-the-box solutions that you get with LabVIEW and their disadvantages. We saw an example of a software based on user events and what is involved in scaling it up. We saw the same example implemented using the AMM, and then we looked at the performance of the AMM as the software scales and its advantages over the out-of-the-box solutions. So thank you very much for listening. Don't forget to install the AMM package through the VI Package Manager. And please get in touch if you have any ideas for improvement. I'd like to point out that the package is not currently available on VI Package Manager because I'm just waiting for it to be approved. So it should be there in a matter of days. So thanks again, and I'd be really happy now to take any questions or any feedback that you might have. Yes, Eric, you can. Yeah, so essentially every AMM is like a small network of applications, and you can have as many as you want. It's beneficial in any kind of applications. So it was designed as a generic tool for any sort of software. Eric, so essentially you can have as many AMMs as you want, so as many separate networks of applications. And this depends on how you want to structure your software. So it's totally up to you, the way you want to separate applications from one another, or the way you want to make them communicate with one another. That's totally up to your judgment. And yes, it's also free. So you can get it through the VI package manager. Obviously, you'll have access to the source code. You can modify that if you want. What I would be really grateful for is if you do have any ideas for improvements, or you end up making any improvements, just to let me know so I can update the version and publish it back for the others to take advantage of it. Yes, you can use it for commercial purposes, yeah. So it's totally free. I'm just curious if anybody is familiar with the actor framework, or have much experience with the actor framework. If you have any ideas how this compares to the actor framework, if there are any things which you think this cannot do but the actor framework could do, I'd be really interested to get that kind of feedback. I haven't done Alifia. I haven't done any tests with multiple AMMs in the system, so I don't know about how the performance changes. I wouldn't expect it to change, especially since they're separate AMMs. Narayana, can you share related documents? What sort of documents would you like? Yeah, I haven't used DQMH yet. Yeah, I've never used it actually. Implemented code. I could, yeah, I could share some examples, but they're really basic, just to show essentially in which order you would call the functions. Narayana, if you want to send me an email using the email address on the screen, I can send you some VIs to as an example. All right. So yeah, thank you everyone. Thank you for all the comments, and thank you for the feedback. I'm happy to see that there are at least a few other people who think this is useful. Right. If you have any other thoughts, any other comments or anything, please feel free to send me an email, and we can continue the conversation via email. Thank you very much. Right. Thanks, guys. Thank you. I can see all the messages. Thanks a lot. Thanks again. All right. Okay. Right. So thank you, and take care, and bye-bye.